Welcome to this module, and in this module what we are looking at how to design a strain gauge, right, for understanding the catheter contact force, and I will show you how this same strain gauge can also be used for understanding the change in the mechanical properties of tissue. Now you have already seen in the last module how the photolithography process, what are the steps for photolithography process, and what kind of photoresist are there, what kind of mask are there. I have taken an example as well, right. So, let us see here how can we design the strain gauge. Okay. So, if you see the screen, what you see here is a 3D MEMS based strain gauge at the tip of the catheter, and we want to understand how we can design this MEMS based sensor for catheter contact force, right. So, this is a MEMS based sensor, and as you can see we are using a square bead. So, you have how many surfaces? You have 6 surfaces, but one surface is used to connect to the catheter. So, we have now 5 surface on which we can stick the sensor. What kind of sensor we are using? We are using strain gauge. So, now as you know how the lithography is done, right, I will show you this particular process, and also I will show you step wise how we can go from step 1 to step 6. So, here if you focus this particular section, right, what is it? The first one is that you take a oxidized silicon substrate, right. The next one is you have to deposit P dot PSS. P dot PSS is a conducting polymer. P dot PSS is a conducting polymer. Okay. So, conducting polymer we have to deposit on which there is a thin layer of silver, right. There is a reason behind using silver is that you have a better adhesion of the P dot PSS on the substrate. Then and that P dot PSS is on PDMS. You should see, so what is the process? Let me just show it to you in this slide. You take a silicon, right, and this is your silicon wafer, grow oxide. So, I have grown silicon dioxide, this is silicon dioxide, and then the next step is on this oxidized silicon wafer you pour PDMS. You have to pour PDMS, all right. On this PDMS, we will spin coat P dot PSS, on which there is a thin layer of silver. So, what we have written is you have silver over P dot PSS over PDMS, right. This is what we have written. Now, if you go to Beck's, then you will understand in this slide that we have written Ag, which is silver, on P dot PSS on PDMS. Next step is you pattern photoresist, right, on this particular on P dot PSS, so as to get the strain gauge. So, how you will do patterning? So, for that what you have to do? You have to spin coat photoresist. So, this is our positive photoresist. Then you have to perform soft baking, right, and then we go for exposure. What exposure we have to go for? We will go for UV exposure, because this is a photolithography, right, and now we know what is UV lithography, right. So, you have a mask. What kind of mask it looks like? It looks like a bright field mask, right. So, this one is my bright field mask, right, and then next step would be UV exposure. After this, next step is you dip the wafer, you have to of course unload the mask and dip the wafer in photoresist developer. When you do that, what you will have? You will have oxidized silicon substrate. Over which there is a PDMS, right, PDMS, over which there is a thin layer of silver, right. Is it correct? It is correct. It is not correct, right, because on PDMS what we will have? On PDMS we have P dot PSS, and PDMS we have conducting polymer, right. So, we have P dot PSS. On P dot PSS what we have? We have thin layer of silver, On silver, now you have done the lithography and you have developed your photoresist. So, what you will have? You will have positive photoresist patterned, right, positive photoresist which is patterned. Now, so this is what we see here. See this particular step we see here, which is pattern photoresist on silver, on P dot PSS, on PDMS. Next step is that you etch silver, this one is silver, and then etch, you etch, this is a wet etching silver, followed by etching P dot PSS, followed by etching P dot PSS. So, what you will have? You will have AG and P dot PSS. AG is a silver and P dot PSS on PDMS, over which there is positive photoresist, right. So, of course, after positive photoresist developing, you have to go for hard bake and then you have to do the etching step. So, do not skip that, right. The process you should know that when you deposit or when you spin coat photoresist, first step is you have to go for soft baking, and soft baking is done at 90 degree for 1 hour, followed by loading the mask, UV exposure, then developer, then hard bake which is done at 120 degree centigrade for 1 minute on hot plate, and then you have to go for etching, right. After etching we have to strip off the positive photoresist. So, for stripping of positive photoresist, what we will do? We will dip this wafer in acetone. If I dip this wafer in acetone, what will happen? My positive photoresist will be stripped off. The positive photoresist is stripped off. So, my positive photoresist is gone. Now, what I have? I have silver and P dot PSS, right. Do I require silver? I do not require silver, right. So, what will I do? I will etch silver now. So, after this acetone dipping, we will dip this wafer in AG etchant. AG etchant. So, silver etchant, if I go for silver etching, what will I have? I will have only PDMS on which P dot PSS strain gauge is patterned. P dot PSS strain gauge is patterned. This step right is shown here. alright. These are the steps that you have to follow. So, as to get the particular pattern of a P dot PSS. Why we have used P dot PSS? Because we want to make a strain gauge, and P dot PSS is not only conductive, but it is a piezoelectric piezoresistive material. You should understand what is piezoresistive and what is piezoelectric, right. You apply pressure, change in resistance, piezoresistive, apply pressure, changes voltage, piezoelectric. Okay. So, strain gauge, once you have the strain gauge, the next step that you see in the glass in the schematic is that you have to have PDMS bump, right, that you attach on the strain gauge. That means, if you go to this slide, what you want to have? You want to have PDMS bump on the strain gauge. So, that this bump will help us or will facilitate the force that we apply on the strain gauge to transfer the force that we apply externally to the strain gauge. Alright. So, PDMS bump, how can we create this PDMS bump? For creating this PDMS bump, we have to perform again a lithography. So, what we will do? We will have a silicon wafer, we will have a silicon wafer. Next step will be to grow oxide, next step would be spin coating positive photoresist. All right. Next step is you have to do a soft bake at 90 degree centigrade 1 minute on hot plate, and then you can load the mask and expose the wafer. Load the mask, it will be a dark field mask, and expose the wafer with UV light. So, this is silicon, this is silicon dioxide, silicon dioxide, this one is positive photoresist, this one is your dark field mask. After exposure, you have to go for photoresist developer. When you do photoresist developing, what you will have? You will have oxidized wafer, positive photoresist, SiO2, SiO2. Then you have to go for hard bake. After hard bake is done at 120 degree centigrade 1 minute on hot plate. After hard baking, you have to dip this wafer in buffer hydrofluoric acid. Buffer hydrofluoric acid is BHF. When you dip the wafer in BHF, what you will have? You will have oxidized silicon wafer, your oxide is etched, alright. So, if the oxide is etched and this is your positive photoresist, this is your silicon dioxide, silicon dioxide, right. Now, if you dip this wafer in acetone, dip this wafer in acetone, what will happen? The photoresist will be stripped off, photoresist gets stripped off. So, you will have this particular pattern, right. Now, after this I will dip this wafer in potassium hydroxide at 80 degree centigrade. This will, when I do this, what will happen? I will have a pit, right. This pit should be equivalent to the height of the bump that we want. So, now you understand this much process. If you go back, you will see, so you take a silicon wafer and you create a silicon pit. This is where we are, right. This is what we have seen here. You take a silicon wafer, grow oxide, spin coat photoresist, right, load mask, expose the wafer, right, go for photoresist developer, hard bake, soft bake, everything we have done. After photoresist, you go for soft bake, which is right over here. Then you go for mask, UV lithography or exposure, photoresist developer, then hard bake, and then you are dipping this wafer in silicon in BHF, which is silicon dioxide etchant. What will happen? The silicon dioxide will get etched. You remove the photoresist with the help of acetone, and then you dip this wafer in KOH to get your pit, which is pit in silicon, and this pit, the depth of this pit is equivalent to the height of the bump that we want. Now, after this, what I will do? I will pour PDMS. I will pour PDMS on this particular pit, and then I will cure it. This is PDMS. I will pour PDMS on this pit and then I will cure it. When I cure it, I can strip it off. If I strip it off, what will I have? I will have PDMS like this, right. Now, if I cut this, then what will I have? I have PDMS bump. Okay. This PDMS bump I have to attach on strain gauge. I have to stick it on strain gauge, right. So, how we can create this PDMS bump is using a lithography technique. That is what is shown here, that you have silicon wafer, this one, you have silicon wafer, grow oxide, create a silicon pit, then pour PDMS and then cure it to form the PDMS bump. This bump you take it and attach it to the strain gauge that you have fabricated earlier. So, this entire PDMS that is here, you can strip it off from the oxidized silicon wafer. So, this is what you get. PDMS, then P dot PSS strain gauge, and then the PDMS on the top, right. This is your sensor. This is your sensor. How? Let us see. Now, if I do that, then this becomes your flexible force sensor. So, if I press this particular sensor, it will bend, and that bending or strain in the sensor will cause change in the resistance, because it is a piezoresistive sensor, right. This is what is shown right in the figure that once you know lithography, it becomes easy for you to understand how you can create a different sensors or fabricate different sensors. This is a recipe, alright, this is a recipe. Now, how to create this particular sensor, right. So, the first step is to take the cube, then the second step is to create flexible force sensor and to attach it on each side of the cube. See here, slide 1, slide 2, slide 3, slide 4, slide 5. Why slide 6? The side 6th we are not doing anything, because the side 6th is the side which we have to attach on the catheter, right. So, all 6 sides, side 1 from side 6 we are side 1 to side 5 we are using for attaching the piezoresistive flexible force sensor. After that, you can perform the simulation. It is very easy to perform a simulation, so as to understand that when I apply a normal force onto this particular sensor, how the strain will be there, and what is the effect of stress and strain on the overall performance of the sensor on applying a force from 0 Newton to 1 Newton, alright. So, we have done this study, right, and we can understand what are the different simulation results. This is the actual photo of a strain gauge made out of P dot PSS on PDMS material. Okay. Now, if I perform the experiments, then first point is I have to understand what is the change in resistance on applying a certain force. So, I have to connect a commercial force sensor or commercial load cell, and then I will apply a known amount of force onto the sensor, So, if I know that 0.5 Newton of force I am applying and my sensor is showing change of resistance from the base value as 20 ohms, then I will know that every time when it shows change in 20 ohms, it is 0.5 Newton. You got it? That is why we are applying a force through the load cell or a commercial force sensor. Once I have the data, then I will, so this is what it is shown here, right, and if I connect the sensor to a proper electronic conditioning circuit, I will show it to you in the next module. Then what will happen, you can see the change on applying a compression force from 0 to 0.1 Newton minus, so from minus 0.8 to 0.1 compression force, what we will have is a different sensor output voltage. Same thing when you are applying on the y direction and z direction. So, x, y and z, and every time you have to fit it, and the fitting value is close to 0.98, 0.99 and 0.997, that is R square value, and thus it is a linear fit. Now, once you know this particular parameter, the next step is to understand the change in the phantom tissue, change in the elasticity of a phantom. Phantom is not real, ghost, okay, phantom tissue. Phantom tissue you can make with the help of gelatin. Phantom tissue you can easily make with the help of gelatin. If you have ate jelly, jelly is what it looks like a tissue, and that is why the jelly would have different elasticity, right. If you eat a jelly bar, you will understand that it is very flexible. So, can I measure the elasticity of the jelly, because it is a phantom tissue, right. So, to that, if I have a fabricated sensor and if I apply force on the jelly, I will see the change in resistance depending on how much force I am applying. Now, I do not know what is the force I am applying, but because there is a change in resistance, I will use this value which I have already have a table with the help of commercial force sensor. If you remember, we are applying different force to our fabricated sensor, from that we have force versus resistance value. Now, with the fabricated sensor I am applying force to the tissue, and that whatever change in resistance is that will correspond to the earlier force. Thus, I have a force and resistance correlation. So, let me show it to you here if it is too confusing for you. So, if I have the commercial force sensor CF, this is fabricated force sensor FF, right. Now, what I am showing you here is that let us say there is an electronic conditioning circuit. So, every time the resistance changes, let us keep resistance as a point. Now, I am applying different force 0.4, 0.1 to 0.4 newtons. Okay. This is commercial force sensor applying force on the fabricated force sensor. Now, when I am applying 0.1 Newton, I am looking at a change in resistance. So, let us say base resistance is 1 kilo ohm. The change in resistance is 1.1 kilo. Now, the new value is 1.1 kilo ohm and applying 0.1 Newton. So, what is the change in resistance? About 0.1 kilo ohm. If it's a linear, then I will have change resistance like for 0.2 I will have change 0.2 kilo ohm, 0.3 Newton I will have 0.3 kilo ohm, 0.4 Newton I have 0.4 kilo ohm values. Now, I know that whenever my sensor is changing from 1 to 1.1 kilo ohm, that means the force that it is experiencing is 0.1 Newton. This much is easy. Now, what I am doing, I have fabricated sensor, force sensor, right, with 1 kilo ohm base resistance, and I am applying a force onto a gelatin. Right, gelatin is a phantom tissue. When I apply certain force, I see that my sensor is showing 1.2 kilo ohm. From this value, I can understand 1.2 kilo ohm, that is 1 plus 0.2, this is delta R what we are showing, right. This is overall resistance. So, this 1.2 corresponds to 0.2 kilo ohm, and that is why it is 0.2 Newton. If it is changing from 1 kilo ohm to 1.4 kilo ohm, 1.4 kilo ohm, when I apply a force on the gelatin, then the change from 1 kilo ohm to 1.4 kilo ohm will be of 0.4 kilo ohm. This 0.4 kilo ohm corresponds to 0.4 Newton. Thus, I know that I am applying 0.4 Newton of force onto gelatin. That is what I meant when I was telling you about the force versus change in resistance and how to correlate it with the help of a commercial force sensor or a load cell, and then go back and press the gelatin tissue, and from there we can get the results. So, this is a MP285 micromanipulator. You have seen the MP285 micromanipulator. You will see probably in the class, but if not, then it is it is used to manipulate the rod that we are attaching or the catheter tip that we are attaching in terms of few microns. You can move it x, y and z with a precision of few microns. So, now when you apply a force, right, onto gelatin with the help of the catheter, then what you get, that you have a sensor output voltage versus calculated contact force, and the sensor measured contact force versus the calculated contact force. So, you can see that it is extremely linear, and thus the sensor can act to as a force sensor. Now, when we apply different grams of force from 5 gram to 40 gram to 60 gram, you can see the change in the sensor voltage. So 40 grams is our optimum force for the ablation, we have seen that. Similarly, if I want to use the sensor in water and I can move the sensor in x, y and z direction, then for that I have different sensor output voltage depending on the distance that I am moving. For each side I will have so for in this particular case you have seen sensor 2 and sensor 1, right. The FZ1 and FY2 would be the force acting on the z direction, like right here, and when it is acting in this direction, the force acting on FY2 will also be there because of the way we have attached the sensor. One sensor is at the tip of the catheter, one sensor is on the side of the catheter. So, when you are applying a force which is FZ1, then correspondingly FY2 will be affected. Same way when we are applying because you can see here, you see what I am saying is this sensor is connected on the side, this sensor is connected at the bottom, alright. So, when I am applying FZ1, this one force is acting on FZ1 surface, for this sensor 2 which is on the side, I will have force on FY2, and when I have force on FZ2 which is right over here, right, I will have corresponding force at Fx1. alright. This is how it is rated. So, FZ1 is related to FY2, FZ2 is related to FX1, Z is Z, okay, FZ1, so I say Z, but you can also say Z, it is how you are comfortable with. So, but the point is here we can measure the change in the voltage, which is the sensor output voltage when we move the sensor in the water. So, this is how we can do the experiments, and this is the last slide for this particular module, but what I want to say is that with the help of lithography system you can design several sensors. One of the sensor I have taught you in this particular module, we can use electronic conditioning system using operational amplifier and connect it with this kind of sensors, so that we can see the corresponding change in the force values at the display terminal. Alright, so till then you have to take care, right. Please focus on the slides, the notes that I have given you, the videos that you can see, and also try to see the experiments, because experiments are extremely useful. If I talk about ECG, you can also find ECG from lots of PPTs available online, right. You can learn books on PCB on the ECGs, but if we are showing you in a real time how the ECG is performed is very different than what you find from the what you can learn from the books, right. So, please focus also on the experiment part, and in the next module we will continue the further topics of this particular course. So, I will see you in the next class. Bye for now.